I'm Dan Jeffery. My background with 3D printing and CNC milling mostly has to do with so an enthusiast interest, somewhat similar to you, although I'm really interested in actually playing with the things. But I also have a background in material science and engineering and archaeology. And so for me, the metals and the changes to metals over time and how we're able to do this is part of why it's fascinating and part of why I'm here.
Awesome. I'm C.R. Rowenson. You can call me Clark. I actually write nonfiction. I help storytellers build, craft, and repair the magic systems for their stories so they support each other instead of damaging each other. I'm here because by day I learned the dark art of chemistry. So I am a chemist and a chemical engineer, and I've spent the past 5 years doing a lot of learning polymer science, developing different polymers for 3D printers and working with a really janky one and making it do what I want every time it decides to do something different. So.
Okay. I'm Brian de Almeida, brought into fandom by my stepmother, Sarah Hoyt. My degrees are automotive mechanics and industrial management. I've worked a lot in automotive, in firearms, and generally kind of a nerd about manufacturing technologies. And so I've worked with practical and theoretical applications on small and large scale.
Nice.
Hey, great. Well, why don't we start off, because I don't know much about it, and I imagine there's a few that don't know much about the technology. Maybe you could spend some time explaining what's available, the basics of what we need to understand.
Yeah. Well, and I think between the three of us, we have the main fields covered. So, why don't you go ahead and do the metal, Dan, and I can do the polymer stuff.
Yeah, let's talk about the metal stuff. So, let's take one step back from that first and talk about the way that 3D printing works. In general, when you're doing 3D printing, what you're doing is you have a contained space that you have control of, and in that space you're using some technology to fixate into a solid form some material that's within the space. Yeah. In some cases, that's going to be a dust that gets frozen or melted into something else that then is locked in place and is able to be used as the new material that it's been fused into. In other cases, you're laying down a thread of a polymer, for example, and then that gets locked into place in the new shape. That's really what most of us are probably most familiar with in kind of the home context, is a filament, or you're laying it down. In the case of metals, there's two methods that are most commonly used. There's a binder jet method, where they're basically gluing pieces of metal together in a complex and robust way in 3 dimensions and building it up. I mean, one of the aspects of 3D printing technology is you've got to plan your way up from one corner or one side and work your way through the structure and build in pieces that are going to attach to later pieces, but everything has to be able to work its way up from some level. And really it's similar to the problems that you have in traditional casting as you're designing a casting and figuring out how the metal is going to flow into the different corners. And then with metal, there's the binder jet approach, and then there's the direct energy vaporization, or vapor
laser sintering.
Yeah, it's basically you're using lasers or other strong energy beams, and you're nailing a powdered metal that then gets fused into the new shape that you want, and you can have really rapid prototyping, etc. That's the metals.
Yeah, the terminology, if you're looking for it, those are mostly, they call them powder bed printers.
Right.
Because your metal is just a container of this metal dust that they fuse together different ways. The polymer stuff is completely different because you're dealing with the plastic in one form or another, and you have a variety of different types of plastic that you can use. So the main types are you have thermoset, you have thermoplastics, and then you have UV or chemical set. And the thermoset means that you heat it up, it goes through the chemical process, and it's done. A lot of your water bottles, you can't melt that down without decomposing the plastic. Thermoplastics are unique that they can be melted down and then re-solidify, and that's what you get in like your MakerBot, your LulzBot, and your standard desktop printers. Is it's something that melts, fuses to the layer below it, and then re-solidifies. So that's thermoplastic. And then the last main version of polymers is the UV or chemical cure, where you'll have that'll be like vat polymerization. You'll just have a tub of goo that they'll shine a light. They'll use a laser with mirror to scope out the pattern and cure it layer by layer with very fine precision. And those are the main types of polymer chemistry you have. I mostly worked with thermoplastics, so.
Okay, you guys have covered 3D printing, so I'll cover CNC. CNC, computer numbers controlled machining, is a totally different process from 3D printing. 3D printing being an additive manufacturing process, whereas machining is reductive.
Yeah,
You start with a casting or a forging in the basic shape that you use, and then the piece is worked by a series of tool heads to give you your final shape in removing void spaces, drilling holes, and achieving that exact desired shape for your finished product. This has traditionally been done manually. Machinists are highly trained, and we're dealing with machines that are running a tool head in 3, 4, 5, or 6 axes, down usually to tolerances measured in the thousandths of an inch. That has traditionally been done by hand. My grandfather was a machinist for Lockheed throughout the 60s and 70s. Actually built parts that went on every Apollo mission. But all of these things were done by hand, measuring everything by hand, and there's an inherent amount of inconsistency that you get with that, even with the very best machinists. With CNC machining, provided that your setup of the piece and of the machine is correct, you get not necessarily tighter tolerances, but you get more consistent results. We actually see that especially in firearms today. Mm-hmm. If you look back 50 years, or actually the first half of the 20th century, firearm parts were made from castings, and then they're essentially made oversized and then hand fitted.
Okay.
Today, we see this most especially with the AR-15, America's rifle, where there's one set of specifications, and there are like 4,000 companies making parts that are all basically drop-in interchangeable with no fitting.
Okay.
And and the primary driver behind that is the consistency that you can get out of the CNC machining.
So, and that's a really big deal, especially with 3D printing, because the tolerances you get with your 3D printing machine will vary from not just from the individual machine. Like your MakerBot will give you slightly different tolerance than your LulzBot, but the different operator.
Yes.
Like if you operate the MakerBot, I go in and do it, the tolerances are going to be slightly different.
Exactly.
Which it's kind of crazy.
Yeah, and the computer control inherent with CNC machining removes a lot of that error, and has done a lot to bring us into the era today of drop-in parts that don't require skilled labor for fitting.
Yeah.
We see that in firearms. We see that we see that in the automotive industry as well, where there is a lot more today of part swapping than there is of actual repairs, and that has been enabled by the precision we get out of computer controlled machining.
Okay. And
So-
Brian, go ahead.
No, I was going to jump in real quick. One of the things that maybe everybody's already realized, but is an important aspect of what we're talking about here, is the time required, right? As we talk about a machinist working through this, somebody comes in with a design they've drafted up and says, I need one of these made. And the machinist figures out the right way to do it. He might have to make different tooling in order to accomplish what he wants. Mm-hmm. He's going to tweak it until he gets it right. And so we're talking hours, tens of hours to hundreds of hours later, and he's got the part that they wanted, and he could do it again faster the second time, but it's still going to be time consuming. We go to CNC, and CNC's faster than that, and it's repeatable really quickly. Similar problems, though, of you've got to get just the right tooling, you've got to tweak it until it's just the way you want it.
You have to have the correct jigs and tooling and setup.
Yeah.
There's a lot of lead time that does require highly skilled machinists, but then your actual mass manufacturing, rather than paying a tool and die machinist $150 an hour,
Right.
which is what some of them make, you can be paying a lower qualified machinist $50 or $60 an hour to
Right.
run the CNC or to run the
Right.
water jet.
Right.
Right.
And then the 3D printing comes
Yep.
in, which I'll let you go. I had that.
I'll
yeah.
keep going. All right.
Yeah.
So with the 3D printing, then you take it to another level where, and let's next, if you're all right with this, talk about kind of the differences and tolerances and some of the pros and cons of where 3D printing is now in this context, because I think context.
And
is really
don't
good.
let us forget about bioprinting. We had a whole conversation before the panel. I apologize, but ask about that later. We'll definitely talk about that more.
So with 3D printing, we don't have to build tools and jigs to do it. We have a space, and in that space, anything that we can design an appropriate pattern for and have it execute that, we can make almost anything as fast as we can tell a computer how to make it.
Yep.
And the advantages there are huge. 3D printing is expensive, but so much time you can save, especially in prototyping, especially in
That's the
iterating on new ideas. Say, well, what if we changed it a little bit like this? Back in the early machinist days, we're looking at, okay, well, I'll make another one, and it's going to be a
You're
while.
100 and you're 100 hours of lead time
Right.
to get that one prototype
Right.
to realize, oh shit, this is off by 3%.
Whereas with the 3D printing, I had stuff at work where we would, you just needed the CAD program.
Yep.
We would sit down, somebody would generate the design in about 30 minutes. I would go print it in another hour,
Yep.
and we would go, in the process of a week, we went through 17 versions, doing small tweaks because we weren't machinists. We didn't know how to do the tolerance measurements. So it was just okay, let's do it again, just a little smaller. But yeah, 3D printing really lets you do that faster generation because you don't need the special tools.
Yeah, and that's where the industrial application of 3D printing is one in prototyping, and two is in small batch shops.
Yes.
We're seeing it's actually revolutionizing the entire market for classic cars.
Yes.
Because you're dealing with small numbers of things, where most traditional mass manufacturing methods, you're looking at hours of machine setup time for each part run. And if you're only making 30 of them, it makes the per unit price extremely prohibitive. With 3D printing, you can have a catalog of GM dash bezels from 1934 up through 2017, receive an order, print it that day, and send it out without any setup time aside from actually creating the model.
And obsolete parts is
Yes.
another big deal because you'll have things with cars or something in your house, or even like helicopters and fighter jets, right?
Right.
They'll have a unique piece that is not being produced anymore, and they can scan it, redesign it, and print it for a fraction. And I'm talking 1% of the cost it would take to have these other people design, build the tooling, and manufacture it for the 10 instances they need.
Exactly.
So
yeah, the small batch stuff is where
Yeah.
the industrial application is really starting to shine.
I mean, if you know that you're going to need enough volume of something that it justifies cranking out 10,000 or even 1,000, then you
other methods
totally
are
go
more
to
economic.
CNC, you go to
Yeah.
castings,
So,
you go to
yeah.
methods where you're
Molding.
duplicating the same thing and it's cheap and easy to do.
So we're kind of just running. Feel free to stop us if you have something.
I was just going to add to this conversation. We're seeing big changes in science. About 3 years ago, they found a cave with a whole bunch of hominids in it, and within a year, they had scanned all of the bones, and you can essentially download a skeleton of one of these creatures for study. You can study it yourself, and you can look at it.
Yeah.
In that would have taken years and years and years before, and we would have looked at photographs. And
Right.
everything. But I can make the skull in different sizes. I can make it full size, or I can
Right.
make it miniature to pass around in class and things. So it's interesting to me.
Yeah.
That's a really cool application.
Yeah.
They've been using 3D printing a lot for education purposes.
Yeah.
Because one of the first things I did is I actually printed, when I was testing our printer, I printed a model of the ocular nerve. Just because, it's something I found on Thingiverse that I downloaded for free and printed it out. It wasn't applicable to my job, and my boss was like, "Why'd you spend time doing that?" But it was cool. So
That's been my favorite application.
Yeah.
3D printing that stuff. That's cool.
So we talked a bit about the real power of 3D printing is it okay if we move into like some of the drawbacks?
Yeah, I was going to say,
right?
what are the
Yes.
limitations, and where are we now? What are these were really good illustrations of how useful it is. What are its limitations? Where is the technology not reached yet?
So we talked a bit about the large scale production versus the one-off, unique customization and prototyping. The other main thing is time, and not labor time.
Not operator time, but
Yeah.
machine time.
But machine time. Because whereas for the machining the part, he said it would take 100 hours of like mapping and drawing and planning, and then the machine would do it in 30 minutes. Whereas 3D printing, one of the other models you can get, you can just find it by searching, is you'll see the Octopus or the owls. That's a really common thing that people like to 3D print. Printing an owl about this big with 30% infill, meaning it's 70% void space, takes 8 hours.
Yep.
It's not fast. It's an owl that tall. It's only about that big around, and it takes 8 hours to print that. Granted, you can do things to speed it up, but the machine time to do it is pretty extensive.
Yeah, but the way economics are the way economics are running, machine time is a hell of a lot cheaper than skilled
Yes.
labor.
Yeah.
So with that you can have dozens of machines that are each running one piece.
Yeah.
And effectively only have one machine operator.
Yeah.
So it's the economics of mass manufacturing are somewhat nebulous, but
if you need to be
drawback
doing,
is machine time.
yeah. If you need to be doing millions of
increases
pieces.
in or speed, has there been some increases in speed? Do you
Oh,
see
yeah.
that projecting to be faster?
And there's some things you can do depending on the resolution of the print you need. Sorry, this is where I'm getting really nerdy because this is spent years doing
They
this.
came to hear
Cool
nerds.
Yes.
That's why they're here.
So getting this validation is just very cathartic. I spent years on this, but like, so you have the resolution that you need to deal with, and the finer your resolution, that means you're printing smaller and smaller pieces at a time. The more time it's going to take. So if you're okay with like rougher 8-bit style owl, you could, if you had nozzles big enough, you could do that in 30 minutes probably. But since we were doing 0.2 millimeter layers, that took hours. That took a full work day.
Yeah.
So, and if you're getting to the level where you need millions, you might be better like looking at using it for casting, using the 3D printing, creating a mold.
Well, and
and
here
going
you're
from there.
talking analog versus digital at that point,
Yep.
really.
Right,
I mean,
kinda, yeah.
it's a very close parallel because you're doing layers and you're doing checks at a time, and so you're digitizing it and cranking it out as a digital thing versus a casting where you're pouring it in and it's much more organic
Right,
in
right.
a analog way. I think one of the other aspects is there have been significant increases in how long it takes, right? We've come up with new tech, and I think it's reasonable to assume that going forward, we're going to come up with better and better ways of doing it. If you look at printing technology and getting to how cheap and fast a laser jet printer is nowadays, just a laser printer. And I mean, I remember even using a laser printer when I was applying for college and thinking, oh crap, I didn't allow myself enough time to get this printed before I have to hand it in, as opposed to now it's like print and 50 pages, just crank out there and you're done.
Yeah.
Right?
Yep.
We'll continue to improve the speed with which that's able to be delivered. And we'll come up with other methods that, like looking at the metal examples again, these applications are not trivial power consumption. Right?
No.
The amount of power required in order to do the powder bed or the directed energy deposition, that's a lot of juice.
You
to
do
crank
metal
these things
printing,
out.
you're going to notice on your electricity bill.
And those are things that we will also improve, right? You look at early laser technology to modern. We use lasers in all kinds of things nowadays, and they have gotten cheap and easy, and we've tuned the right amount to get what we want. The components of the 3D printing systems themselves get cheaper as we move to mass production
Yeah.
of 3D printing systems. So, I mean, all of those economies of scale as it's used more and as we improve the technology will come into play.
Yeah.
And it will get cheaper and it will get more common. But there will always be trade-outs that we're making.
And there's always going to be a limit, right? We're going to approach an asymptote where it's
Yep.
just
Yeah.
We've got, okay, that's as far as we can push this
Diminishing
tech.
returns.
And until there's some
To the
concept
point where
that is a
investment
dramatically
is
different
not-
approach.
is not worthwhile.
Yeah.
And one other thing that I want to mention, because from where I came from, there's there's a lot of upset, which this is kind of pushing into some other stuff you had talked about, Steve, that concerns of the impact on industry. We had a lot of people being like, 3D printing is awesome, so now we're going to use it to replace everything.
No, we aren't.
No, it doesn't work that way. So
It simply does not work on economies of scale.
and even design, there are designs that you can do with 3D printing.
Yep.
That would be a nightmare with CNC or any other milling. So like, I meant to bring it. We printed this little cube that just had four holes drilled across from all sides that were perfectly rectangular channels. Milling that
That would be a nightmare.
But that took us 90 minutes to print.
Or I got a Christmas gift from a friend. It's a octopus about this big with the front 5 tentacles flipping the bird at you. At the detail levels down to probably a 0.5 millimeter.
Oh yeah, have fun machining that.
That was run off on a printer in 20 minutes. In order to create that out of plastic yourself, you could get a rough shape, and then you're dealing with artisan level work to get down to the fine details.
But there's the flip
Which
side
is
of that.
hours and hours.
Yeah, there's the flip side of that, where there's a number of shapes and designs that are still easier with industrial and milling methods. So one of the ones I talk about a lot, especially with polymers, when you're doing thermoplastics, you have to deal with the cooling time and the thermal dissipation, that kind of stuff. So there's something called overhang, which is the angle you can build outward without having support. And if you go over a certain angle, it's going to slump and it's going to break and you're going to lose that. So there's limitations on the designs you can build with 3D printing that don't exist for milling. So like doing these bevels where it comes in, flat cut, and bevels out real sharp, you're not doing that with 3D printing, not without printing support material.
Yeah.
So-
Yeah. Good. Yeah. I mean, think De Laval nozzle for a rocket motor.
Yeah,
Hell of a lot easier to machine that on a lathe than it will be to print it.
and faster.
Yes.
Yeah, I mean it takes again, like we said, more man hours to design, but once you have it done,
Once you got all the tooling, I mean, it's design and it's the tooling. The tooling is a huge
it's
part of
design-
getting it
yeah.
working.
Yeah.
Design, it's essentially building the manufacturing
Yeah.
process for the first
For
time.
it in the
It's
first place.
hugely expensive part of any mass manufacturing.
but to take this to like a ridiculous level, you're never going to print a table out of plastic because you can just mold the sucker. Like you
Yes.
can just melt it and pour it. Why would you spend days printing this thing and gluing it together?
See,
Because you can.
Okay, that's fair.
you make it so that it clips together like Legos.
That's fair.
So I think one of the things that comes out of this conversation is, and this is what has happened with us with various other technologies in the past, is we will see things that CNC and milling and casting were trying to do and struggling with be taken over by 3D printing, like prototyping
Yes.
and some complex shapes, and certain things will become, man, 3D printing is a better way to do this, and that's what will happen at an industrial level where we're looking at optimizing for what's best for us, right? And then the other areas of milling and casting will become even more specialized in the
Yes.
things that they do well, and they will stop trying to do the things that they were struggling with that 3D printing just took over. And they'll be able to do what they do well even
Yes.
better than they do it now, because the focus will be there. This is the direction we take these technologies. So the technologies will find the right niche to coexist and flourish.
Right.
And then, but as we talk about the home use case, as we talk about what we do at our houses and what we want at our homes, that's almost always going to be more of a prototype situation.
Yeah.
It's almost always going to be a situation where we'd be better off if I can just find the right pattern and download it, because I don't even know how to tell the computer to make what I want to make.
Right.
I just want that pattern, and I get the pattern, and I send it over wireless to my 3D printer that's next to the fridge or whatever, and I can make the cool new coffee cup that my buddy showed me or whatever.
And
Right?
I want to come back to that because I know one of the things they wanted us to talk about was the home use. But Steve, you had asked specifically about where this would go, like 20 years, 100.
Yeah.
Like, real quick, the main thing Go
Let
ahead.
me elaborate on that, because what I see is with the ease of this type of technology, it may be a move to modularization, so
Mm-hmm.
that you build the Legos, for example, for complex
Right.
things.
Yeah.
Not literally Legos, but the
Figurative
modularization,
pieces, yeah.
so that
Yeah.
so that manufacturing actually starts moving to what you can do with
Right.
printers rather than that. So go ahead.
Yeah, and that's you get to an interesting point where you have to take the technology and blend it with what we already have.
Yep.
Because you took me in a completely different tangent from where I was going to go.
Oh, sorry.
But, no, this is good.
Go ahead.
Because part of what Dan was saying with, like, I can go and download it. If you have people who know how to calculate the tolerances, you can have 12 different groups design the different parts of this machine, build it to the same tolerances, ship it to one place or 12 different places, and as long as they match the tolerance profile, you can build them all and come together and they will reliably fit together.
Yep.
Which is so cool.
Yeah.
Yeah.
And future applications. Say at home, we're going to reach a point where certainly with household items, it is going to be cheaper to purchase a license to the design and print it at home.
Yes.
Than it will be to have it made elsewhere and then shipped to you.
Yeah.
And
Okay.
we're to the point where that's actually practical. We're probably 20 to 30 years out.
Yeah.
But it's wholly reasonable to expect that most of us, well, at least we know when I'm old, will probably have some sort of home manufacturing capability where it's just expected you're going to hop online and purchase a license, purchase a software license
Yeah.
to print 5 copies of this design and do
that's
it at
it.
home. And then of course we run into the bugaboo of piracy.
So,
And
Oh, man,
how
that's so
and,
neat.
and how do you control and how do you control the whole economics of purchasing designs rather than discrete objects?
and one of the things on that, you may not know this, but we have the tech and we have the materials that if I had the machine, I could 3D print a tennis shoe.
Yeah.
Like rubbery, soft-soled tennis shoe. Like all going to be plastic with different gels and foams and stuff like that. But that's there. But I'm going to forget, so I want to... Sorry, there's so much fun stuff. Where I was going to go about 5 minutes ago was for the progression of technology, and I found this applies to like any new technology. There's always the fear that it's going to take over what we already have, but that's not how it works.
Yeah, how often has that happened?
Yeah, it's always an augmentation to the weak parts of what we have.
I mean, even if you go as far back as copper and iron.
Oh, yeah.
Right?
Yeah.
Iron replaced many of the things that copper did eventually, but copper still has important roles to play and began to fit into other niche capacities.
And copper did not replace woodworking.
Nope.
Carpentry is still a thing.
The automobile did
We
not,
still use
did
rocks
not
for
wholly
counters.
replace the horse.
Yeah. So that was one of the main things. Like that's a really cheap
that's a good
approach
one.
to your like 100 years.
Yeah.
But just don't think that one technology is ever going to wipe out all other technology.
Well, unless we actually get Star Trek replicators.
That's what I was going to ask. They were replicating a guitar
I don't know.
at one point, and I thought,
I-
far away.
I will argue it's going to be the same argument,
one
though,
area
right?
I wanted to go actually, that, because for me, looking at metals, right? You think about this home manufacturing printer that we're talking about right now, or even in industrial applications, you still have to have the right materials
Yep.
Yes.
in order to be able to produce what you're talking about.
Not magic.
So, and when we talk about metals in particular, we get into really complex things around
Yes.
different alloys that we need. And with metals, there are many times other stages. With a plastic, you might print it and say, bam, we're done. That's all we're doing to it. But with a metal, it's going to be really common, especially for a wear piece or something that I want to be springy or perform in particular ways. There's going to be heat treatment cycles. There's going to be other stages that need to happen to this piece that at this point we don't do inside the 3D printer because it's a whole different set of temperature problems and installation issues and whatever else. And maybe we'll get to the point where you have an all-in-one 3D printer that I print the metal and then it cooks it up to the right temperature and then it cools it the right way. I mean, that'd be really cool and incredibly expensive, and we don't make those things even
Again.
as it is, because we make them different pieces because it'd be so difficult to combine into a single thing.
There are a lot of high strength metals applications where it's highly unlikely for printing to replace anytime soon. For example, firearm barrels.
Yeah.
The ways you look at the cold hammer forging process of making a rifle barrel, you have a mandrel with the rifling on it, and the steel is actually formed by repeated high pressure hammer falls on it over thousands and thousands of times around to create that desired shape at the exact dimensions that you need it. But a big part of the reason that cold hammer forging is used is because of the way the process affects the crystalline structure of the metal, and enables it to handle high temperatures and high levels of pressure.
Yay, metallurgy.
Yes.
Yeah.
Metallurgy.
Come at 6 on Saturday for the metallurgy lecture.
Which on that note, like, you're not even going to be 3D printing a sword.
Oh, hell no.
Like,
No.
the
closest
strength,
you could get.
you could get a sword shaped.
You could get something that's the right shape, but and maybe we could get to the stage where there's enough consistency with what we've laid down that we could then just do the heat treatment on it. Maybe we could get to there,
Possibly.
but the heat treatment has to be done. I mean, if you look at something like the directed energy deposition stuff, maybe you could get enough consistency that you don't have voids and you don't have other
Theoretically, yeah.
problems.
Maybe,
but,
yeah.
But most of the time, with something like a sword, for example, or a knife, it's a tool that you're putting a lot of faith in, and you need it to perform in critical situations. And in those situations, you want to know that this thing's going to perform the way you expect it to and not fail on you. So there's going to have to be a lot of investment before people would begin to trust that this is something I'm willing to use. But those post processes, those handling processes of, well, now I've got it in the right shape, now I've ground it to the shape I want, now I have to do crystal structure in metal is huge. We need to take it from this, it's been heated up for pounding, and then heat it into where now we've, say just in a simple knife making process. You heat it up to a certain temperature that's soft enough that you can whack it with your hammer and it acts more like clay and gets to where it's supposed to be, right? Or you put it into a mold with a power hammer or whatever in a more industrialized process. And once it's the shape you want it to be, then you grind it so that it's going to come out to be all of the right. And maybe before you grind it, you might even do a heat treatment process to soften it back up a little bit. But then once it's ground to the shape you want, you're going to put it in an oven and you're going to heat it a few times to try and normalize the structure of it. And then you're going to take it, cool it really good, and then you'll heat it up again and freeze it to change the structure again. We're talking layers and layers of changes that are not trivial to do.
And this is to make a knife.
Yeah,
So-
and in blades, it's not a single heat treat process either, because you want the spine of a blade to be rigid, while the edge requires a certain I've got this backwards. The edge needs to be hardened. There needs to be a certain amount of flexibility in the spine, or else the damn thing breaks when you whack it.
So I think they made a mistake putting the three of us together because we're just going all over.
We're going
to
45 minutes.
So
apparently it's not
3D
long
printing.
enough.
Should we allow questions? Should we let them ask some questions?
Yeah. So 3D printing.
Oh,
All right.
Or well, sorry.
You're the moderator. You can pick people.
Yeah, we're just
okay, go ahead.
we're just so excited. We're taking your job away. Sorry.
It's basically for you because all this metallurgy thing is like, I know I'm a blacksmith.
Awesome.
So,
Come over. We'll hit some stuff together.
Yes.
my point is
Are we all blacksmiths?
when
Are you blacksmith? Sweet. All right. Well, we're going to talk afterward.
when is realistically metal 3D printers going to be publicly available?
They are right now if you have enough money.
And the power source.
Yeah.
Yeah.
It's dependent on
But the
economics.
price is coming down to where you can really do. I don't know the time frame on that, but I would think that within the next few decades, you will be able to do. I mean, you already see some stuff when we talk about firearms printing. There's a lot of interest from people in iterating, and I mean, okay, I'm in a tangent, just super fast, but the use case specifically of firearms printing. there's a lot of really fascinating innovation that can happen with 3D printing of firearms that's been limited by the traditional processes. So that'll be really interesting to see what kind of weird proliferation we get as you know,
that's not even
any Joe Bob
considering
can.
the political effects.
Yeah, well,
of some of this.
those guys.
So the one thing I will say about that, the biggest limitation with metal printing currently is the structural integrity of the pieces you print. So that's going to be the biggest drawback for some time. Is right now anything you metal print is not sturdy.
Right.
Like you can do stuff that is higher, but they, when it first came out, you could crumble it because it was a jet where it would just spray
the binder
glue.
jet stuff. I mean, there's the three different. I said there were two, but as I look closer, there's three different methods that are used for metal. Right? There's the binder jet, and basically you're just gluing pieces of metal together.
Yeah.
So that works if it's like for a decorative handle piece or something, and
that
it's
would
done
crumble.
well enough.
That would crumble under your hands.
Well,
so
it seems like they've gotten stronger with the binder jets, but
and they would also migrate bronze into it. Which I thought was super cool. But anyway,
so there's cool stuff, and then you get into the powder bed stuff, and you've got something that's more solid because it was fused together with heat.
Yeah.
But you still end
But
up with
tensile
gaps and
strength is still
voids.
a huge
Yeah.
issue.
It's not at all the same thing as if it had been truly melted and poured into a casting. And then as you get to the directed energy deposition stuff, again, you're using higher. It's more focused on truly metal applications, but there you're getting to the most expensive and the highest energy consumption approaches in order to try and get metal right. So really getting to where metal is easily a home tech is years down the road still.
and
But
if you're using it for design, you're probably better off with vat polymer to get the shape and the design, and then going and blacksmithing it yourself. And that's
or doing cast. I mean, if you're going to do lost wax and stuff, you can totally do.
You can totally do home casting.
Yeah, you can
So-
use it for making really cool castings.
it
but,
depends. We didn't really give you a good answer. Probably a while.
Yeah,
well, if I had that crystal ball, there'd be a lot of other problems I would have solved in my life.
yeah, right.
Hey, in the back.
Lottery.
Right? Then I could buy a directed energy deposition.
Is it possibly practical, or is it more of a hobby thing?
I'm sorry, ask it. I didn't hear the first part very clearly.
3D pens, are they practical, or would they be
Oh,
more?
the pens.
Oh, yeah, the ones where you write it. So I've worked with those. The issue you run into that. Okay, so we're gonna go. Or do you write science fiction? Or
No,
fan
I'm
of science?
more of a fantasy guy.
Okay, so the main way, in my experience, this is me just doing my conjecture because I'm a nerd, whatever, is if I wanted to do sci-fi, would be doing it in some sort of thick and congealed substance, because the main problem you run into with the pens is you run out of support. So you build it up, and then you stop, and then it falls over, right? You can't just draw it like on your tablet and be like, line, rotate, line, fill, board. You don't get to do that. You have to build a base and build from that. That's the biggest problem I have found with the 3D pens.
Which makes for a rather steep learning curve to get anything useful out of it.
Now, if we had a little zero-G chamber, that'd be great.
Well, but I mean, with the pen, you
Then there's a
basically
lot
have to
of
do
other
this.
stuff we'd be doing first.
It's true.
I mean, with
Zero
the
G chamber, I call first dibs.
That's
with the
fair.
pen, you basically have to do the same thing as if you were the 3D printing
Yeah.
chamber.
Yeah.
It's really a matter of, yes, it's free form, but you've got to do it the same way you'd have to do it if you were doing it inside of a box.
You get to skip the CAD software.
That's
Yeah.
Yeah.
You had a question, I think?
Yeah,
And-
for the
and we'll
conversation
go back
to
here.
continue, what are your favorite forums or video channels, workshops, like a makerspace, would you direct us to?
Are there any good makerspaces here in the area?
I don't.
I know there's one
I'm
in
not
Salt
from
Lake.
here.
Okay.
So
I know there's a good one in downtown Salt Lake. If you're from this area, I don't even know if you're from this area, but makerspaces are a great way to continue the conversation, and there are several places online to search for them. I can't remember what they are off the top of my head, but you bring up makerspace, and many makerspaces do have 3D printing and people that'll teach you how to use it and encourage you to do crazy stuff.
I
There's a promo
use
called
I
Polymers.
use
there?
shapeways.com for on demand printing of occasional stuff that I do.
in terms of forums to learn about it, you can check out RepRap, REPRAP, and that's a specific type of printer, which I'm just going to nip this in the bud because people get very excitable. They call them self-replicating printers, and it's not what you think. So They call them that because you print pieces that go on the printer. It's not because they're sentient and make more of themselves. You can't even print the whole. Yeah, you can't even print the whole thing. There's metal components that need to be machined and sent to you. So when they say self-replicating, bear that in mind. But RepRap printers, there's some really good forums on that. If you want an idea of the types of things that people can make, check out thingiverse.com. That's all just models that people have uploaded that you can download for free. And that's actually where I've gotten a lot of my stuff, and kind of what Dan was talking about that we didn't get to go back to is just the free sharing, and what Brian mentioned that we didn't get to go back to. The free sharing and the copywriting and the piracy of, I created this tool and he just stole my CAD file.
Yeah.
So he technically just stole intellectual property.
Good luck proving it.
Right? So
Yeah, good
Right
luck
there?
getting any compensation.
Talking about like asymptotes and like limits of the technology in the future in regards to polymers, because it sounds like that's the big rate limiting factor. Is
Material
how quickly
science.
do these polymers congeal and the like where do you see it reaching kind of a point where okay, we're not going to get any more improvement out of like time and quality with polymers?
So are you asking like what is the fastest we think it'll get to, or
Essentially, yeah.
or are
How
you
much
wanting to know
improvement
more
do you
about the
expect?
problems to get there?
Not the problems, like how close are we to, okay, this is the fastest we can print this because of how long it takes the polymers to set.
Okay. So I've been talking a lot, so I don't want to just immediately jump in if you guys
You're
have
I'll
something.
take a
Polymers
second.
guy.
I'll take 1 second and then hand it over to you.
Okay.
Because my background is in material science, and polymers are a big part of material science. There's been a lot of research into. I think taking one step back for just a second, talking about how polymers really work is a great
Yes.
idea here. We've talked a little bit about thermoplastics and thermal polymers that are but basically a polymer is a bunch of molecules that form a cross-linked chain, right? And various forms of linking, but
It's
we link
spaghetti that sticks together. That's
yeah,
what-
and how we link them is what really defines a lot of the properties of the polymer. And if we link them, and so some of the traditional ways we've done it is like have a puddle that we've poured into a shape, and then we apply a particular acid or whatever to it, and all of a sudden they all change into something else and interact with each other and gain the properties of the new structure that we've imposed on them. And before they weren't a polymer; they were, a liquidy goo, and the polymerization process is what caused them to turn into a solid thing that is what we want. So 3D printing changes the game a little bit in terms of how we approach that, because a lot of the traditional stuff was with liquids like I just described. But as we try and start with something that's semi-solid in the first place, so there's a lot of the research focuses on, well, what are photo reactions that we can induce? How can we, because there have been studies of this already, and we know UV has massive effects, but if we can say, and then also the stability, how long do we need it to be stable?
Big deal.
And
And
when do
under
we
what
want it to
conditions?
change again? Those are massive factors as we talk about polymers, because there are things that we can do that'll make it stay that way for 5 minutes or a year or 10 years. But if we want stuff that we want to function for 50, it's a big deal.
So
All right.
it's a really good question and a really hard question to answer. In general, with what we have, we're really what it is it's optimizing. Which from where we are, I can't even give you a percentage, but it's not going to be drastic. It's not like we're going to go from hours to seconds.
So it's not like we're out here, we're more like over here.
Yeah, we're kind of here, and there's things that you can do with the design of the machines and with a bit of the polymers that can change that. So I wanted to hit some of the key things that make it difficult with the polymers. When you're doing a thermoplastic, if you're building a solid piece, the conductive cooling becomes a big problem because the heat, in order for it to solidify, it has to cool down. And with all of the stuff on the outside, your center is going to remain gooey for a long time. So getting the machine and all that set up so that it can cool properly and quickly is actually a really big challenge. And then doing it so it doesn't interfere with the nozzle and the feed through. And with any polymers, so this is another tidbit about polymers in general, what you get is usually not fully cured. The reactions that are going on to make those cross connections usually aren't 100% complete. It's chemistry. It's actually going on indefinitely. It just slows down. So we can do things to speed up the process, The problem there is, like, we actually did that with one of ours. We adjusted the polymer so that we could print it and get specific mechanical properties, but over time the cure kept going, and it went from being nice and flexible and gummy to being really brittle. So
You see this actually a lot in early plastics from like the 50s.
I think we ran.
Are we done?
We out of time, right?
We're close.
I
think we still got 4 minutes.
Oh,
Do we?
Yeah, so
that's my bad.
let's ask one more question.
And then I'll give each of you a minute to give a final.
I was just going into the firearms. I've seen that they're looking at, some people are looking at printing 3D printed lowers. I've also seen carbon fiber impregnated filament.
Yes.
Is there any advances that are going on there?
Well, 3D printed lowers are already a thing.
Oh yeah, which part of the way that's going to work is design centered around making the receiver, the actual serialized and regulated part, not essentially a non-weight bearing or a non-stress part, because then you're not running up against hard limits on tensile strength. We already kind of did that with the AR-15. For the most part, the lower receiver, the actual serialized part, is not a wear item. It is not very dependent on strength, and so it works.
So on that, my grandpa used to say you don't need a parachute to skydive, you need a parachute to skydive twice. You don't need strong material to fire a gun. You need a strong material to fire it twice. So a lot of the 3D printed guns you see, those are one-shot apps.
Yep.
They go and it's done. And you fire it again, you're probably going to get fragments in your hand. So it's something else.
But I think the AR lowers are an example where you can have AR lowers that are reliable for multiple uses because it's not.
I know a guy who does three gun competitions specifically using a polymer 80 lower for both his Glock pistol and his AR receiver.
I think
Just to test them, and we're the ones
environment,
we're the ones running around blasting shit and javelining our rifles into a barrel as we're running at full speed.
I think it's safe to say if you want to know more, like, we'll talk for hours.
Our time's gone. Just maybe a final comment by each panel member on what you're excited about.
I'm excited about where we're going with metals. That to me is the most fast. The polymer stuff is really cool, and there's neat things we're going to be able to do there. But the day that I can put a 3D printer that handles some really cool metal stuff, I mean, for smithing, if I could just have the 3D printer crank out, my cross pieces and my pommel nuts for me, that'd be a nice day.
Oh hell yeah!
Where can we find you?
At my house.
You guys need to bring business cards.
I've got some,
I don't have an easy way to get in touch with me. Honestly, I don't run a website. I just do my job and mess with
So
stuff.
come get his email later.
If you do want to keep in touch, I'm happy to do that, and I would be happy to give you my email. That's fine.
I'm most excited about the polymers and all the fills that you can do, because I can talk for a long time about that, but you can change the properties in really interesting ways. You can find me at my website, which is just crrowenson.com. I have a blog where I talk about all magic systems all the time, and as far as I'm concerned, that includes advanced tech and monsters, just all that stuff. I love it. I won't shut up about it, but I will now.
For me, the biggest thing is impact on mass manufacturing. Mass manufacturing is one of the coolest things that we've done as humans in the last century. And the way and seeing how the industry is going, how things are trending is really cool, and then trying to predict it. Really, the only place you can find me is Facebook, because my personal life's kind of a mess and it's been very busy. But you can look me up as Brian Almeida on Facebook.
Let's thank our panel.